So now let us proceed to find the instantaneous forms of the same equations. The instantaneous, which is with respect to the time, fields, instantaneous fields of the plane wave in a lossy medium are, let the E be curly in order to represent the instantaneous form of the electric field, is actually equal to real part of E with respect to y e power j omega t, and that is equal to E1 e alpha y cos omega t plus beta y plus E2 e power minus alpha y and cos of omega t minus beta y. Likewise, the magnetic field instantaneous form is real of h with respect to y e power j omega t. So just putting the value of h gives me h1 e power alpha y, the same way cos omega t plus beta y plus h2 e power minus alpha y multiplied with the cos omega t minus beta y. Since the particular solution contains only a plus y traveling wave, we only have, the solution we considered, this one, the one we considered is having only a positive y directed wave. So the direction of the propagation of the wave is only in y direction. That is why we are going to consider only the positive directed wave, and E1 and H1 obviously goes 0, right? Because for this case there is no negative y traveling wave, there is only positive y traveling wave, so which is represented by E2 and H2 in fact. So so we can say then E of z with respect to y is actually equal to E2 e power minus gamma y, right? Okay, so now, or you can say that E, let it be a bit bold, if this is representing a vector of y, is actually equal to E2 e power minus gamma y, and the unit vector is az. Likewise, is hx of y is actually equal to h2 e power minus gamma y, or you can also say that if we have a bold h which represents the vector, then the magnitude of the vector is h2 e power minus gamma y, and the direction of the vector is ax, which we knew from this example, the one we considered. So now, in order to find out the phase velocity and the lambda for both the cases, let us go on. So as we did previously, that the phase velocity can easily be calculated for any wave, but this time it is omega by beta, and previously it was with respect to k, omega by k in the lossy case. So this is for lossy medium obviously, and for the lossless, if you remember, we did it for lossless medium, and that was phase velocity was Vp equal to omega by k, where k is the wave number. But now obviously this beta, you have to note that the phase constant beta defines the phase associated with the plane wave propagating in any lossy medium, right? The resulting equations for the wave parameters are, number one is phase velocity, and the wavelength is actually now equal to 2 pi by beta. And if we talk about the wave impedance, then the wave impedance, which we did in the previous case as well, is actually derived from this equation. Curl of E is equal to minus j omega mu h. The same way we did for previous lossless case, you can also derive the wave impedance of this particular case we are considering in a lossy, the plane wave in a lossy medium. We can derive it to be equal to E2 for this particular case, E2 by H2 obviously, and it is actually coming out to be j omega mu if you solve it for this particular case. I'm omitting many steps over here obviously. I consider you go through the steps we did for the lossless medium, right? And now it is the lossy case. So j omega mu divided by gamma instead of k, and this end up with j omega mu divided by under the root of j omega mu and sigma plus j omega epsilon. And you can also say that this E2 by H2 is in fact equal to the wave impedance obviously, and the value for this is j omega mu divided by alpha plus j omega epsilon. Don't get scared with this. This eta represents the wave impedance, and as I told you that if you put the values of mu and epsilon to be that of the air, this gives you the wave impedance of any wave traveling in air, right? So the air in air it is normally 377 ohms. It's nearly 377 ohms. And how can you find this? By just putting the value of mu as mu naught and epsilon as epsilon naught. This was in the lossless case we did previously, right? So but in this case, the lossless medium, the plane wave can travel, and this is the impedance being offered by the lossy medium, in which sigma shows the conductivity of that medium, mu the magnetic properties, losses, and the dielectric losses of that particular medium. So that's it till now. We don't be scared with the equations. What we are trying to understand is how the waves can be categorized and can be put in equations if you are considering a lossless medium or a lossy medium.